Good morning, class. The session is being recorded. So again, make sure audio video is muted. And for the sake of privacy issue, you can even change your name to your initials. We are looking at 3.8 differentials and linear approximation. We have covered every section of the chapter, and we are going to look at this last section in the chapter. Again, differentiation formulas, many of them you got to be very comfortable with because we are getting to applications now. Logarithms and the properties were discussed, and as you can see here, it is extremely important to be comfortable with logarithmic properties. It is very important to be comfortable with logarithmic properties to be able to differentiate logs. So as you can see here, many properties were discussed in general. This is for common log, this is for natural log, and these are the equations that give rise to differentiation formulas for natural log. Okay, and of course, if the base is different, this is what we use. And now we want to look at the new material, differential. So let's discuss the concept. So the very first thing that I want everybody to understand is just paying attention to this graph. Okay. So for y equals f of x, the x called the differential of x, and we denote it by dx or delta x. In other words, the good old run. This is the same thing that we have seen run. This distance, which is the same as this distance, delta x. In other words, x plus, as we move from x to x plus delta x, it covers the distance of delta x along the x-axis. Now, we have a dy, which is called the differential of y, and it's equal to f prime of x dx. Okay, for a continuous function, which is a differentiable function, for small delta x, delta y may be difficult to evaluate. We have approximated with dy. So what is delta y? What is dy? As far as the graph is concerned, take a look at this curve, everybody. As we go from x to delta x, along the curve, we cover the rise of delta y. Rise of delta y. As we go from x to x plus delta x, along the tangent line, here's the amount of rise, okay? AB or dy. They are different values, but I hope you see that dy and delta y, which are completely different values, they become close if delta x becomes small, and they become closer and closer as delta x gets smaller and smaller. So okay, this is A, this is B. So dy is AB. Let's call this C. And delta y is BC. And we are not saying the two are the same. They are absolutely not. But they are fairly close. And that's the idea. Now, take a look at what happens here. We know f prime is dy dx. So if we treat this as a fraction, dy is f prime of x times dx. dy is precisely equal to that. So you have a way of calculating. Delta y is rise along the curve. And it's precisely equal to f of x plus delta x minus f of x, this distance. Okay, class, remember this is f of x plus delta x. If you subtract f of x, so if you, this is f of x plus delta x, this is f of x. If you subtract this dashed line from this solid line, you get the distance of BC or delta y. So take a look at delta y, take a look at dy, and how each one is calculated. Delta y is not equal to dy, but it's approximated by that. Now, delta y is equal to that. If I move the negative fx to the other side, becomes delta y plus f of x. So f of x plus delta x, precisely f of x plus delta y. This is precise, exact. We said f prime is dy dx, and therefore dy is f prime of x dx. We can replace this with dy, and that becomes an approximation. Okay, everybody? That becomes an approximation. Also, linearization. Linearization means just find the tangent line, class. Okay, finding the tangent line. That's all. And that means we use the point slope. Now, of course, if I move the y1, it gets plus y1, which is the same as f of a. Okay, you can use this formula, but understand, just stick with the point slope, and you're fine. Stick with the point slope, and you're fine. Okay. So here's the first example. We want to go through that. If f of x is 4x cubed minus 3x, and dy and delta y are to be calculated, we start with dy. To get to the dy class, just for now, ignore it and just differentiate f to find f prime of x. This is easy. We can find f prime of x. Okay. So we find f prime of x, which is 12x squared minus 3. Now to find dy, just write the same thing and put a dx next to it. Class, dy is the same thing, put a dx next to it. To evaluate this, we need x and dx. X is what? 3. Dx or delta x is what? 0.2. This is elementary algebra, of course. This is 9, and this is 108, minus 3 is 105. You do the math, you get 12. So dy has this formula and this value. However, we can also calculate the precise value for that, which is delta y. And what do? Use this formula. And what is x is 3. What is delta x is 0.2. We want f of 3.2 minus f of 3. Now, this is elementary. Plug in 3.2, evaluate it. Plug in 3, evaluate it. I'm not going to go through that. You just plug in, and you get 22.476. 22.476. Now, as you can see, this is not the same as this one. This is an approximation of that. And one might say, okay, there is a large difference between the two. Here's the reason. Delta x compared to x is large. If delta x is small compared to x, we are in good shape. Okay, everybody? Because it's large and therefore there is a difference between the two. There's a huge difference, I should say. Here's the next one. The radius of a blood is given 1.4 millimeter, the radius of blood vessel. So right away, the blood vessel and the radius, it's got to do with circle, okay? The drug causes the radius to change to 1.3 millimeters. Use differential to find the approximate change in the area of a cross section. So this really gives it away. You're looking at a circle. So you need to know a piece of information about circle. Everybody knows the area is pi r squared. So what is the radius? It is always the original one, class. Original one. Or the first one. And the change takes place and it goes to 1.3. Now the change is delta r or dr or delta x. In this case, x is not the independent variable. And it is important to pay attention to the sign. Because it goes down, it's negative. If it goes up, it's positive. So r is the original 1.4. dr or delta r is the new one minus the old one. Again, if we go from 1.4 to 1. Let's say 7, then it moves up by 0.3. Okay. So whatever the new one is minus the old one. Why is this important? Because it gives us a sign. What does it mean? That area is changing, but what? Is it going to get larger or is it going to get smaller? Because of this, it will get smaller. And again, a is pi r squared. We need to calculate dA. Why are we calculating dA? Because it says use differentials to find the approximate change in the area. We will discuss the exact. They haven't asked, but we will discuss that. So with that being the case, in order to find dA, first we need to find a prime of r or dA dr, which is pi times 2r or 2 pi r. Now, so we need to find a prime of r, which is dA dr, and then dA is the same thing times dr, just like this one. dy is f prime of x dx, so dA is a prime of r dr. Okay, everybody? And so pi r squared gives us 2 pi r. So what is dA? The same thing times dr. And now plug in r is 1.4 millimeters. The units are important. dr or delta r is negative 0.1 millimeters. And when you do the math, you get negative 0.28 pi millimeters squared. The area and the differential, they have the same units. And the reason is because this is 1.4 millimeters and this is minus 0.1 millimeters. So that's why it gives rise to millimeters squared. Okay. And 2 times 1.4 is 2.8. With 0.1 makes it 0.28 pi. If you insist to replace the pi with its approximation of 3.14159, whatever, you get negative 0.8796 millimeters squared. Now, what if the question wasn't using differential to approximate the change, rather it was find the exact change? So the blood vessel goes from 1.4 millimeter to 1.3. find the exact change in the area of a cross section. Now you use your formula that you have here, A equals pi r squared. You plug in 1.3, gives you the area, new area. You plug in 1.4, gives you the old area. Their difference is the exact change. I have factored out the pi. The product of these two is the new area. The product of these two is the old area. Their difference is what we are interested in. And take a look at this one with the pi, and take a look at this one with the pi, and see how close they are. Okay, and because negative 0.1 or positive 0.1 makes no difference in this case, is fairly small to r, which is 1.4. Therefore, the two numbers are very close. Okay, that's how it works. Let's look at the next one. We are interested in the following. A bacterial colony has a population of P of t is 20t over 10 plus t squared in millions t hours after the nutrient is introduced. We want to use differentials to approximate the change from t equals 2 to t equals 2.4 hours. Okay. So in essence, we want this one where the function is P of t. Okay, so we really want P prime of t first, which is the same as in essence dy dx. We want P prime of t. And then dy becomes dp, which is f prime times dx, now P prime times dt. That's the idea. Okay. And then so we need to know the original one. The original one t is 2. And the new one is 2.4. So dt is 2.4 minus 2, or simply 0.4. Okay, and pay attention to millions. Okay, that has an effect. And so we need to differentiate this. So we need to find P prime of t. So given P of t, we need to find P prime of t, which is the same as saying dp dt. P prime of t is the same as dp dt. And then we find dp, which is P prime of t times dt. P prime of t times dt. That's what we are looking for. So to differentiate this, let me just remind you. Okay, so this is your f function, this is your g function, and we use f prime g minus g prime f over g squared. And so with that being the case, here's what we do. We differentiate the top, 20 times the bottom, minus we differentiate the bottom times the top over the bottom squared. So 20 times 10 plus t squared minus 2t times 20t over 10 plus t squared. This class is 200 plus 20t squared minus 40t squared, and it simplifies to that. So what happens? We are going to say dp is the same thing times dt, and replace the t with the original t, and dt is positive 0.4. Okay, everybody. Of course, you just plug into a calculator. This is 4, and this is minus 80. This is 4, this is 14 squared over 196. Okay, and so you do the math and you end up with 0.245. And because it's in millions, that means this one, which is the same as 245,000. Now, if I were to come up with the exact, basically, I would plug in 2.4 and then I would plug in 2. Their difference is the exact. So take a look. And that means 189,000. And why the difference? Take a look. 0.4 delta t is fairly large compared to t of 2. And that's why the difference is more than expected. Okay. But if this was like 0.1 or 0.01, then the difference would be negligible. Okay. Oh. We are interested in approximating 51 squared. First, let me just quickly remind you, if you want to square that and you want to do it in your head, you can use algebra as follows. 51 squared is 50 plus 1 squared, which is 50 squared. 2 times 50 times 1 plus 1 squared. I'm using a plus b squared. So in your head, you can come up with the answer of 2601. But how do you use the differentials? You need two things. First, you need a function that mimics this. So all you have to do, ask yourself, what am I doing? What is my operation? 51 squared. So you say, I want a squaring function. So f of x is x squared. That's the function. F of x equals x squared. Then you want to look for a number, okay, which is very close to 51. And it's easy to find its square. So first you need a function. That would be f of x equals x squared. Then you want to choose a number extremely close to 51. And squaring it is easy. And I hope everybody knows that number would be 50. And since we want to go from 50 to find 51, we are going up by 1 to make sure everybody understands what we mean by this. This one, we know the answer. In essence, this is the original one. This is the new one. If I want to go to, let's say, 48 squared, then delta x or dx equals -2, meaning when I calculate this and I want to go to 51 squared, this must be larger than this. But from here, when I calculate and I want to go to 48 squared, this negative, it ends up being less than that when you square. So going through the process, first and foremost, we need to find f prime. That's simple, 2x. Okay. And then we need dy, just put the dx next to it. Okay. And now the formula that we had here, f of x plus delta x can be approximated by f of x plus dy. So your f of x is x squared, your dy is 2x dx. Okay. Okay. Let's replace the x with 50 and dx with positive 1. And as you can see, this is extremely close to 2601. Why are they close? Because number 1 is very small compare to number 50. If you compare it to number 50. Okay. Linearization. That means finding the tangent line class. So given the function, if you want 51 squared, the closest number to it is 50, so you find the tangent line at x equals 50. I hope you realize at x equals 50 means the pair is 50 and 50 squared. And now you find the line using the point slope. But what is missing is the slope. What is the slope? If you replace this x with 50, becomes the slope. Okay, so f prime of 50. So just plug in. This has been moved to that, so we're really using the point slope, everybody. Okay. Simplify. This is the tangent line. We call it L or L of x. What do we want? 51 squared. Replace the x with 51, and it gives you exactly the same answer. So differentials and tangent lines will give you exactly the same answer class. I hope everybody's okay with that. How about a similar question? This time we want to approximate a square root. Again, we need two things. We need a function, and we need a number very close to 27 where we know its square root. Square root of 27. So f of x is square root of x. 1 square root of 27. The closest number is 25. We know the answer is 5. So first we want the function, then we want to choose a number. And that number is 25, because we know the square root of 25 is 5. So if we choose 25, delta x is 27 minus 25, because from here we want to go up. Again, just to make sure we understand why. If I want square root of 24, then delta x is 24 minus 25 is negative 1, okay? Meaning, as I go from here to here, the result must be larger, because 27 is larger than 27. If I go to here, the result must be smaller, because this is negative. So we need to find f prime of x. We've done this many times. And then dy becomes the same thing times dx. And here's f of x plus delta x. So f of x plus delta x needs f of x, which is delta x, and needs dy. To find dy, differentiate 1 over 2 square root of x. We've done it many times. If you want, just rewrite this as x to the power 1/2 and differentiate times dx and put it in here. So again, I'm doing this because we have done it many, many, many times. So by now it shouldn't be a surprise. Plug in. Plug in x equals 25 and dx equals 2. So square root of 27 is f of 27 or f of 25 plus 2. So we are here. And now here we're going to plug in. As you can see, 2's cancel out, and square root of 25 is 5. And when you add them up, you can write them in any format. Okay, class. It's pretty straightforward. And just for the sake of argument, if we were interested in finding the square root of 24, we do exactly the same. And this 2 changes to -1. Okay, everybody? Okay. We, in a manufacturing process, we are interested in the following. Ball bearing must be made with a radius of 0.6 millimeters, or the maximum error of this much, 0.015 millimeters. I'm going to use differentials to estimate the maximum error in what? The volume. And I hope you realize ball bearing is in the shape of a sphere. Therefore, we need the volume, which is 4/3 pi r cubed. And because of the estimate, we really need dy, or in this case, dv. So what is given is the radius, original radius, and then what is given is dr or delta r. So original radius, delta r or dr. The volume formula, we should know this. Anyways, I've gone over that. This is a spherical shape, ball bearing. And we are interested in dv. So first thing first, let's find dv, dr, or v prime of r, which is 4/3 pi is a number. Don't touch that. Times, now r cubed gives us 3r squared. 3r squared. And therefore 3 and 3 cancel each other, 4 pi r squared. This is dv, dr. In this case, r is the independent variable. Therefore, dv becomes the same thing times dr. And practically you're done. What is r? 0.6. What is dr or delta r? 0.015 plus minus. So you plug in. By the way, this one, just to let you know how this is done, this is 0.6. 6 times 6 is 36. 1 decimal, so it creates 2 decimals. 0.36, because you're squaring. So you multiply those numbers. Here's with pi. Here's if you approximate the pi as 3.14159. So that's the dv using the differentials.